All right. So last time we just started uh, unit 5 functions. We discussed pretty much in detail in a more formal or abstract definition of functions. And we just started part B of this section. I called it 5.1. In the book, just the 24th topic. So in the second part of this section, we discuss piecewise defined functions. You already learned it before in pre-cal, but we just define piecewise defined functions in a little different way, although we are talking about the same things. As you know, everything we talk about in these courses, both courses actually, we are based on the sets. Everything is related to sets, and we do the same thing for functions, and we can do it for piecewise defined functions. So let's just talk about this theorem 13. We have two sets, A and B, and suppose that the set of P, Q, two elements, one is P and Q, and the other is Q, and both of them are just subsets of A. So it is a partition of set A with two parts. The set P and set Q are disjoint, and the union of P and Q is set A. Okay, so that's what it means by partition. You can make any partition for set A, and the size of P and Q can be very different. Okay, so given this sets, if we are given a function g from P to B and a function h from Q to B, then we can define a function by taking the union of the two functions g and h, and we call it f, which is from A to B. So this theorem that tells us how to define the piecewise function, basically. So in the normal way, we see in pre-cal, the piecewise defined function will be written as this. F of A is equal to G of A if A is in Q, and is equal to H of A if A is in Q first. F of A is taking the value of G of A, which is defined given when A is in P, and we take the value of F at A when A is in the set Q, we take the value from the function H of A. So G and H are both given. So this F is well defined, is defined in this way. Okay, so the theorem says the union of these two functions, G and H, defines another function. We're using the definitions of functions from the sets of ordered pairs to prove it. Okay. So we just do the proof using the most general concept in the in algebra by sets. Okay. So in that way, you consider the two functions G and H given in the theorem by ordered pairs. or a subset of P cross B. Okay, so remember G is from P to B, from P to B, and H is from Q to A. So so G is a set of all the pairs of subsets of P cross B. Remember the Cartesian product of two sets is a set of all the pairs where the first element comes from set P and the second element in all the pair comes the set B. And you should take all of the elements from those two sets to make the other pairs. And that's defined as P cross B, the product of P and B. The function G is defined from P to B. That means you take all the numbers or elements in the set B and paired with elements in B. For each of element in P in set B, you paired with another element in set B. But you may not take all of the elements in B in the codomain, maybe larger than the range. There are some elements in set B not paired with any element in set P. So that's a function. So this function G as set all the pair is a subset of P cross B. All right. And obviously that's a subset of A cross B because P is a subset of A. Remember, set A is partitioned by two sets P and Q. So P is a subset of A. So when you take the product, then this A cross B means all the other pairs of A, B, where A is from set A and B is from set B, including all the elements from those two sets. So obviously set P is less than set A, so it does not have all the other pairs in A cross B. So that's a subset of A cross B. So G is a subset of A cross B. That means. Similarly, H is a subset of Q cross B. Remember, H is defined from Q to B, and also this is a subset of A cross B because Q is a subset of A. PQ is partition of A. So this P cross B is a subset of A cross B for a similar reason. So that means H is a subset of A cross B. So that both G and H considered as collections of all the pairs, as we just said, If you have two subsets of A cross B as a set, if you have two subsets of that, you take the union, it's still a subset of A cross B, okay. But both G and H are subsets of A cross B, all right. In fact, G is equal to the set of all the pairs X, Gx where X is in P, and H is the set of all the pairs of X, Hx where X is in Q, all right? So then you take the union of these two, G and H, as sets, okay? So then F is a subset of A cross B, as I said, because both G and H are subset of this A cross B. So if we take the union of two subsets of a set, then the union is still a subset of the big set. So F is subset of A cross B. So that means F is a relation from A to B. So, that's the definition of relation. A subset of A cross B is called a relation, remember? You just take the sum of the elements in A paired with some elements in B. And, you get a bunch of all the pairs. You can, define any such kind of collection of all the pairs as a relation. So it's a relation from A to B. But function is a spatial relation where each element in each element in the first place of the order pair is paired with a unique only one element from B. Okay, so to see that F is a function, it is suffices. It suffices to check that each element of A is the first coordinate of exactly one order pair in F. So each element of F. So this is F should include all the other pairs for all the elements from A. But each element of A can only be paired with a unique element in B. Okay, so we need to show that, but it's easy to show. Okay, so let's just pick up element in A, and we are going to show, it pairs exactly one element in B. So because A is partitioned in two parts, P and Q, in the problem, then we consider two sets. A is either in P or Q or in Q. Okay. So let's just assume A is in P, and you can prove the same way when A is in Q. So so this without loss of generality. So because A is the first coordinate of exact one order pair in G, remember when A is in P, G is defined from P to B. Okay, so A is the first coordinate of exact one order pair in G, okay, namely A, GA. And we use the fact that G is from P to B, and it's a function. Okay, so that's it is the first coordinate of exact one order pair in G. All right, because it is a function given. On the other hand, it's not the first coordinate of any order pairs in H, obviously, because A belongs to P, so it's not in Q. H is defined from Q to B. All right, yeah. Since every order pair in H has first coordinate in Q and A is not in Q, right? Okay, so that means AGA is the only one order pair in F. Okay, it is the first coordinate of exact one order pair in G, and it's not the first coordinate of any order pair in H. So it is AGA is the only one order pair in F that has first coordinate A. All right. So that proves that F is a function. Okay. And because A was arbitrarily chosen from set A, so this proves that the new defined function of union of G and H, which we call F, is indeed a function. Okay. It is an obvious fact, but we still need to prove it for mathematics regard regardless reason. So let's do some examples. The first example, we have, set A and set B. Set A is the union of two sets P and Q, where P has three elements, 1, 2, and 3, and Q has also three elements, 4, 5, and 6. And B is the set of three elements, 1, 2, 3. That's the same as P, but we call it B, okay, to avoid confusion in this function notation. So then PQ is a partition of A because it's the union of P and Q, and the PQ is disjoint or disjoint. Okay, so this makes a partition of A, and then we can define a piecewise defined function from A to B. So to do that, we're going to define a function G from P to B and another function H from Q to B, as stated in the theorem. Okay. So, for example, we can define G from P to B as G of X equal to 4 minus X. Okay. And define H from Q to B as H of X equal to X minus 3, and then you can actually write down the explicit set of G. Remember, a function is a set of ordered pairs, as we said many times. So G is from P to B. So for each of the elements or numbers in P, we need to find out G of X, which is in B. Okay, set B. So when X is equal to 1, P has three elements, 1, 2, and 3. So when X is 1, G of 1 is 4 minus 1, so that's 3. So that's the first order pair in G. And when X takes the value of 2, G of 2 equals 4 minus 2, so that's 2. So 2, 2 is the another order pair. Okay. G. And when X is 3, G of 3 is 4 minus 3, which is 1. I guess I'm going to mute. Okay. So when X is 3 in P, then G of 3 is 4 minus 3, which is 1. So that's the third pair. So that's all of the other pairs in G. All right. And it's from P to B, of course, as we just said, because if you look at the numbers, elements in B, there are 1, 2, 3, and we got 3, 2, 1. So this three numbers, 3, 2, 1, are in set B. So it is a function from P to B, and similarly, you can find out the set H as other pairs. For example, H is from Q to B. Okay, defined from Q to B. So you take each value of numbers in Q, substitute in this formula. So H of 4 equals 4 minus 3, which is 1. So we get the 4, 1 as first order pair. And when X equal to 5, H of 5 equal to 5 minus 3, so that's 2. So 5, 2 is the second order pair. And when X equal to 6, H of 6 equals 6 minus 3, so that's 3. So the three order pairs is 6, 3. So that's all. Okay, that's all. And if you look at the second element in order pairs, there are 1, 2, 3, which are all in B. So it is from Q to B. Okay. So by using theorem, we can combine G and H, or take the union of G and H as all the pairs to define a piecewise defined function. We call it F from A to B. Okay. By this rule, F over A equals 4 minus A. So that takes the value of G when A is in 1, 2, instead of 1, 2, 3, A is in P. And it takes value of H when A is in the set of 4, 5, 6 in Q. Okay. When A is any of 4, 5, 6, which is Q. So that's A minus 3. So that's H. Okay. So we define the piecewise function this way. I just take some different formulas in different part of the domain A, right? Anyway, so we can represent this function graphically to view it, more directly. So this is set A. It has 6 numbers, 1, 2, 3, which is P, and 4, 5, 6, which is Q, and set B only has 3 elements, numbers 1, 2, 3, and the function g from P to B is given by or represented by red arrows. Okay, so 1 maps to 3, 2 maps to 3 maps to 1. If you look at all the pairs, 1, 3, 2, 2, 3, 1. So this is the function g, 1, 3, 2, 2, 3, 1. And the other function h is from Q to B is defined as the formula of 4 minus x, I believe. X minus 3, I'm sorry. X minus 3. So all in all the pairs, we already wrote it here. 4, 1, 5, 2, 6, 3. 4 maps 1, 5 maps to 2, 6 maps to 3. Okay. So this is the diagram showing the mapping from A to B. And when we take the union of the G and H, and we get another function from A to B. And the red arrows correspond to function G, and the green arrows correspond to the function H. So you can easily take the union of the 2 other pairs, 2 sets of other pairs, G and H, and get F. Okay, so this is the 6 other pairs, all right, corresponding to this diagram. All right, very straightforward. Okay. Let's just do some more examples. Sometimes you want to make sure, when we define a piecewise function, it is defined correctly. So the following question is asking what's wrong with the following piecewise defined function. If we try to define a function f from R to R, from real numbers to real numbers by this formulas, fx equal to x squared plus 2 if x is greater than equal to 0, and fx equal to -1 if x is less than equal to 0. So what's wrong with it? You see, x equal to 0 appears both in the 2 formulas. So that violates the definition of a function. You cannot have 2 different values. When x is 0, if we use the upper one formula, you get 2, but you get -1 when you use the second formula. So 0 in the domain has two numbers paired with 8. So that's not a function, but there's a fundamental reason why it's not, even even if you get the same number from these two formulas, it's still not defined as a function. Okay. It is because the partition of the domain, so domain is all real numbers, and you partition it into two subsets. One is the subsets of numbers, non-negative numbers, x greater than equal to 0, and the other part is x less than equal to 0, which are non-positive numbers. Okay. And this partition is not correct because they're not disjointed. X equal to 0 belongs both subsets of R. So it is not a partition of the domain. So that's the reason why you cannot, f is not a function, okay? They overlap, okay? You can never write two equals, in this case, even if you get the same function value in the two different formulas, you still cannot write two equal signs in both sets. Okay, just keep in mind. All right. We don't need to explicitly say that the conditions given to define piecewise defined function will partition the domain. Usually it's obvious, but as we saw in the previous example, it is actually not. So we have to check sometimes. So we must, however, be careful that the conditions really do define the condition. All right. Let's see some more examples. The next example, we're trying to define a function from z to z by piecewise. Okay. So fx equal 3x plus 1 if x is odd. So fx is x over 2 if x is even. Okay, so how do we know this is well defined? There's nothing wrong with it. First, when you partition the domain Z by odd and even integers, they are disjoint, and the union of them is the whole set Z. So there's no problem for the partition part. Secondly, you want to make sure the function values are in the codomain Z. All right, the codomain is also Z, and we see that's also the case. 3x plus 1 when x is integer, of course 3x plus 1 is an integer, so it's in Z. And when x is even, x of 2 is also integer, so that's also in Z. So in both formulas or both cases, the numbers lie in the codomain. So that's pretty fine. All right. So it is indeed the defined function. All right. So for example, if 1 equal to 4, so 1 is odd, so 3 times 1 plus 1, that's 3 plus 1 is 4. And if 2 is 1, 2 is even, so 2 by 2 is 1. Okay. So that's one example. And the next example, we define another function, piecewise defined function from R to R, from real numbers to real numbers, by 3 pieces. So we just partition the whole domain of R into 3 subsets. The subset of x less than -1, subset of x greater than or equal to -1, less than equal to 1, and the subset of x greater than 1 or 1 less than x. And this partition is correct. There's no overlap for any two of them. And also the union of these 3 subsets is the hold them all. So that's pretty fun. Uh, so so this function is well defined, and the partition is actually three sets, as I said. X belongs to R, X less than 1, X belongs to R, X greater than or equal to -1, less than equal to 1, and the set of X belonging R 1 less than X or X greater than 1. So if you try to plot this function, it will have three pieces. The first piece corresponds to the region of X less than 1, and the Y value is -1. Okay, so that's horizontal line below the y-axis, not include the endpoint, the -1 for X. Okay, and the second part is for X between -1 and 1, include both endpoints -1 and 1, and the function value is 0, so y equal to 0. So that's the x-axis from -1 to 1, including the two endpoints. And the third part of the graph will be in the region for x greater than 1. Okay, so that's on the right. Not including the endpoint of 1 for x. And the y value, the function value is 1. So that's a horizontal line about the x-axis, not the y-axis, I'm sorry. The first piece is also a line below the x-axis. Okay, so it'll be like this. All right. So three pieces. One piece in the middle from -1 to 1, including both endpoints. So we use the closed dots. And the other two parts of the graph, one on the right and one on the left, the one is below x-axis, one is above the x-axis, both parallel to the x-axis, but not including endpoints for both of them. All right. So that's just like a step function, although it's not actually a step function. It's like a step function. Okay. I guess we're gonna stop here. Only 2 minutes left. So any questions?
No.
All right, let me just okay, I need to wait. I don't know what's going on here. I need to stop the recording.